All right, welcome back everybody. In this video we're going to talk about material from section 7.8 of AP Calculus, exponential models with differential equations. We start here with a little narrative. You know, there are a lot of situations in mathematics and sciences and economics, etc., where the rate of change of a quantity is proportional to the quantity. And for every single one of those situations, we can model that in a very similar fashion mathematically. So if the rate of change of the quantity y is proportional to the quantity y, that leads to this differential equation. The change in y with respect to time is equal to some constant times the value of y at the moment in time. Okay, that's exactly what that's saying. The rate of change of a quantity is proportional to the quantity, where k is our constant of proportionality. And the initial value of y here is y sub 0, y at time 0. If we take this separable differential equation and this initial condition, we can use separation of variables. We just got done spending the last two lessons talking about separation of variables. We can use separation of variables to find the equation for this function. So we separate our variables, we integrate both sides, we solve for y, we get y equals ce to the kt, and then since the initial value of y is y sub 0, we can substitute this in, and we end up with this relationship right here, y equals y sub 0 e to the kt. So anytime where we see a problem scenario where the rate of change of a quantity is proportional to the quantity, it will result in an exponential function of this form. This is what we call the law of exponential change. If y changes at a rate proportional to the amount present, then y equals y sub 0 e to the kt. If k is greater than 0, we've got exponential growth. If k is less than 0, we have exponential decay. And this number k is what we call the rate constant of the equation. Okay? All right. Now, one thing that you can pull from this is that if you have a scenario that's modeled with a differential equation like this, with this initial condition, we in essence can always write it as, we can just substitute these values. Instead of going through the separation of variables every time, we could just go straight to this equation. And you'll see what I mean when we look at our first example. All right, example 1. Find the particular solution to each differential equation. First, dy dt equals 8y, and y of 0 equals 3. If I separate this and integrate, I get dy over y equals 8 dt. I integrate both sides, have the natural log of the absolute value of y equals 8t plus a constant. I raise each side to the y power, or e to that power. Turns that into this. And then the absolute value is absorbed into the constant. And then when I substitute for the initial condition, I put 0 in here for t, and I end up solving and finding that that c is equal to 3. And so this is our equation representing this situation. Notice the constant from our differential equation is the constant that is in our exponent, and the value of the initial condition, if t is 0, that's going to be our leading constant. So looking at the next example, dy dt equals negative 6y, and y of 0 equals 5, I can shortcut my way to this equation. My equation would be y equals 5, because that's the initial condition at time 0, e to the, and my constant from my differential equation is negative 6. And so that makes this equation y equals 5e to the negative 6t. All right. Part C of this example, an animal weighs 2 pounds at birth and 3.2 pounds 3 months later. The animal's weight is increasing at a rate proportional to its weight. I'm going to set up a differential equation for this scenario, and we're going to figure out how much the animal weighs when it's 5 months old. So first of all, I'm going to use W to stand for weight, and when we see the animal's weight is increasing at a rate proportional to its weight, that means that dW dt is equal to K times W. Okay, now we're told here that the animal weighs 2 pounds at birth, so that's our initial condition. At time 0, W equals 2. Okay, so that means that we can set up this equation. We don't know what k is yet. We're going to figure out what k is in a moment. But we can set up this equation, w equals 2, since 2 is my initial condition, e to the kt. And our model is going to look like this. Now, what we need to do is use this one other value that we have. Since we weren't told the value of k, we need to use this other value to solve for the value of k. So 3 months later, the animal weighs 3.2 pounds. So W, 3.2, the weight, is equal to 2 e to the 3t, or 3k, pardon me. I divide both sides by 2. Take the natural log of both sides. And I find that k is equal to the natural log of 1.6 all over 3. And so my model here is W equals 2e to the natural log of 1.6 over 3 times t. There's my differential equation for the scenario, or pardon me, there was my differential equation. Here's my actual function. Now, how much does the animal weigh when it's 5 months old? We're going to put 5 in here for time. And this turns into this. If you don't like that as a value, you can always go and calculate out a value. This is going to be 2e to the 5, where's the log? There's a log. 5 log of 1.6 over 3. Close my exponent. And this is 4.378. With 4.377 also being acceptable with truncation. Okay, continuing on. Example 2 here. A radioactive element decays in such a way that 80% of the sample remains after 5 days. And we've got 2 questions to answer here. Question number 1, what's the half-life of the element? And question number 2, how long will it take for 90% of the sample to decay? Okay, so we're told here that the radioactive element decays in such a way that 80% of the sample remains after 5 days. So we don't know how much of the sample there was to begin with, so I'm going to let y sub 0 be the amount of the sample initially. And it decays in such a way that 80% is left after 5 days. So setting up our equation, 80% of the initial value is left. And we've got y sub 0, e, and time is 5. So we could put 5 in for t and substitute k. And then we can solve for and find the value of k in this equation. We divide both sides by y sub 0, and we get 0.8 equals e to the 5k, taking the natural log of both sides. We end up with that, and then k is equal to the natural log of 0.8 over 5. And so the main part of this question is we want to find the half-life. Well, the half-life is how long it takes to get to half of the original amount. So we're going to set up half of the original amount is equal to the initial value times e to the natural log of 0.8 over 5 times t. And we want to solve this for t, and that will give us the half-life. I divide both sides by y sub 0. And then I take the natural log of both sides. And I solve for t. And there's my half-life. And if you want a decimal, you can go ahead and punch it up. I've got 5 natural log of 0.5 divided by natural log of 0.8. And I get 15.531. And my unit here is days. Okay. How long will it take for 90% of the sample to have decayed? Well, in order for 90% of the sample to have decayed, that means 10% of the sample is left. So we're going to go ahead and put 0.10 y sub 0 into this model. And we'll do the exact same calculations we did when we were finding the half-life. We're just going to find the value of time that makes this true. I divide both sides by y sub 0. And I take the natural log of both sides. And then I multiply by the reciprocal. Notice how I do all the algebra and then I just punch it up at the end. You're much better off this way. It's better for you to do it this way than to calculate values for natural log of 0.1 and natural log of 0.8 along the way. Just get what t is equal to and then do one calculation in the end. 5 times the natural log of 0.1 over the natural log of 0.8. And we get 51.594 days. And that's how long it took for 90% of the sample to have decayed. All right, that's how we can use separable differential equations in exponential modeling to build a model from given information. Okay, go ahead. There's plenty of practice problems for you to try out on this concept. Go ahead and do those. And that's it for those of you in Calc AB. This was our last lesson of the unit. For those of you in BC, we've got one more section left. So you can come back for section 7.9. For those of you in AB, you're going to want to start reviewing Unit 7 and get ready for your Unit 7 test. All right, that's it for today. Have a great rest of your day. See you next time. Bye-bye.